Hi everyone, welcome to lesson 25 of the Advanced Higher Stats course. In this lesson, we'll be looking at the slope parameter test. By the end of this lesson, you should be able to do a two-tailed slope parameter test. Here is an overview of the slope parameter test. So you'll be testing if the population slope parameter is non-zero. Basically, what that means is that you'll be testing that there is a gradient or a relationship between the two variables, so that when you input your linear model, it will be useful for predicting. So your hypothesis will be you're assuming that right now it's zero, but you're going to test to see that it's not zero. Your assumptions are that the errors are independent and they are normally distributed with constant variance. So the errors, they don't increase or decrease at any point. You will find the test on page 6, but there are other pages as well you need for the test. And when you're done with it, it will be a t-test. When you're done with it, you will, say that, oh, at this percent level, you have evidence. And in the end, you have to say that the model appears to be useful for prediction. But if t is below the critical value, you would say there is not enough evidence to suggest that. Now let's move on to an example of a slope parameter two-tailed test. So the first thing we have to do is write our hypothesis, which would be h naught is beta equaling 0, and h1 is beta does not equal 0. Now, we need to use this formula here. T is equal to b times square root of s double x over s. So what do we need for that? We need b. To get b, we need s xy and s double x. And then we need s as well, which requires SSR, and SSR requires S double Y, S double X, and S XY. So I've already covered how to calculate these in lesson 16. So we'll skip straight on to the actual calculating the test statistic. Okay, so I'll explain what I've done here. I've calculated the sum of x, the sum of x squared, sum of y squared, and sum of xy, which we've already done in lesson 16. Then I calculated s double x, s double y, and s xy by using these formulae here. Then I calculated b, which is sxy over s double x. So sxy 25.5 over s double x 17.5, and we got our value there. Then we need s. So for s, we need SSR first. As I've done here, I've used this formula here. So s double y minus sxy squared over s double x, which gives us this value. We input that into our standard deviation formula, and then we get this value here for s. And now we can actually calculate our test statistic. Now we have our values to find our test statistic. We have b, s, and s double x. So let's go straight onto it. T is equal to b, which is 1.457, times the square root of s double x, which is 17.5, over s, which is 0.2927, and that gives us 20.82. Now we can find our critical value. So for that, first we need our degrees of freedom, which is 1 minus the number of values we have. So we have 6 values here. 1, 2, 3, 4, 5, 6. So it's 1 minus that, which is 5. And our significance is 5%, and it's two-tailed. So we go into our table here. Degrees of freedom is 5. It's two-tailed, so we'll go for this one here. And that is at 5%. So the critical value is 2.571. Now we can say that 20.82 is greater than the critical value. Therefore, significant evidence at 5% significance to suggest the linear model is or can be used for prediction. And that's all there is to it. Now you should be able to do a two-tailed slope parameter test, and you should understand its assumptions as well.